Problem number 1 here is an existence and uniqueness problem. Pay attention to the fact that it's asking us where the theorem cannot be used, and we're given our initial x, but we're not given y naught here. That's what we're asked to find, what y naught cannot be to guarantee existence on the interval containing 2. So remember, to start, we need to find discontinuities on both f and f sub y, and we treat f as this equation here. So f equals square root of x minus y. Obviously, here you can't take the square root of a negative number, so y has to be less than or equal to x, and that means that y naught has to be less than or equal to 2, because 2 is our given x back up here. Then we take f sub y, and taking the derivative of that with chain rule will get you 1/2 times x minus y to the negative 1/2 power, with a negative because chain rule. And then I like to rewrite that as negative 1 over 2 root x minus y. Obviously here this is stricter because we cannot have a 0 in the denominator. So that means that y has to be just less than x, and therefore y naught has to be less than 2. This condition is stricter than our one up here, and this is where we can satisfy the existence and uniqueness theorem. So in order to find where we cannot, we take the opposite of that, which will end up with y naught is greater than or equal to 2, which is answer choice C. Problem number 2, you should right away recognize that this is a linear differential equation. I first always like to rewrite this as y prime plus 1 over 2 times 1 plus x y equals 6. And now we can go straight to finding our integrating factor here. Remember that will be e to the integral of this coefficient here. So e to the integral of 1 over 2 times 1 plus x dx. When we integrate that, that will get us e to the 1/2 natural log of 1 plus x. And log power rules tell us that this can become e to the ln 1 plus x to the 1/2. You always want to cancel out any coefficients here, because now that means we can go ahead and cancel out the e and the natural log, and rho is just equal to 1 plus x to the 1/2. Now go ahead and multiply your entire equation by your integrating factor. So you'll get y prime times 1 plus x to the 1/2. This will become 1/2 times 1 plus x to the negative 1/2, because it cancels with the 1 on the bottom, times y. And then this will be equal to, let's move this over, this will be equal to 6 times 1 plus x to the 1/2. Go ahead and recognize the product rule happening on this left-hand side. So this is actually all equal to y times 1 plus x to the 1/2 prime. And then copy down your right-hand side. Go ahead and take the integral of both sides, so that'll just leave you with y times 1 plus x to the 1/2 equals 6 times the integral of 1 plus x to the 1/2 dx. When we go ahead and integrate that, pulling down 3/2 will give us 4 times 1 plus x to the 3/2. And remember your plus c here. We can now go ahead and isolate y by multiplying by 1 plus x to the negative 1/2. So this will just leave us with 4 times 1 plus x plus c times 1 plus x to the negative 1/2. And now we've solved for y. We're given an initial condition which we can use to go ahead and solve for x. So we know that 2, because our initial condition is y of 0 equals 2. So we're going to plug 0 in for x and know that's equal to 2. So 2 equals 4 times 1 plus c times 1. So 2 equals 4 plus c, and that obviously gives us c is equal to negative 2. We can go ahead and substitute that back into our initial y. So y is equal to 4 times 1 plus x minus 2 times 1 plus x to the negative 1/2. And we're asked to find the solution for y of 3. So I'll move that up here. Y of 3 going to be equal to 4 times 1 plus 3 is 4, minus 2, and we'll write that as 1 over root 1 plus x, so 1 over root 4 is 2. And then that leaves us with y of 3 equals 16 minus, cancel out those, 1. So y of 3 is equal to 15, which is answer choice D here. Number 3 is an Euler's method problem. I always like to set these up as a table. You can do it with just the equation if you want, but I find the table helps me stay organized. I'll set up a column for x, y, y prime, and delta y. And we're going from 0 to 1 in steps of 1/2, so our 3 points will be 0, 1/2, and 1. We know from our given condition that y of 0 is equal to 1, and now we can go ahead and calculate y prime using our equation at x of 0, so just y prime equals 1 plus 0 squared. I'm just plugging these values into this equation, and our y prime here is 1. To find delta y, we just multiply y prime by our step size, so that'll get us delta y equals 1/2, and we know now that our new y is our y plus delta y, so y equals 3/2. Again, we go find a new y prime. That's going to be 3/2 plus 1/2 squared, so 3/2 plus 1/4 is going to be 7/4. Again, multiply that by our step size of 1/2, so 7/8 is our delta y. To find our new y, we add 3/2 plus 7/8, so that will be 12 plus 7 over 8. That gets us 19 over 8, and that's what we're asked to find. We're being asked to find y of 1, so there's 19/8 is our answer, which is choice B. Here we have a salt tank problem, so the first thing that we need to do is set up our differential equation. Remember that dx dt, where x is your concentration of salt, is always going to be equal to your rate in times your concentration in minus your rate out times your concentration out. So let's start plugging in what we know. Dx dt is going to be equal to our rate in is right here, 5 gallons a minute, so is equal to 5, and our concentration in is given to us here, brine containing 1 pound of salt per gallon, so our concentration is 1. And then minus our rate out, it says that the well-mixed brine flows out at the same rate, so that means it's also flowing out at 5 gallons a minute. And then this is the slightly more confusing term. Your concentration out is going to be equal to x over 100. This x is because this is the amount of salt that we have in the tank, and because our rate in is equal to our rate out, there are always 100 gallons in the tank, so our concentration is equal to the amount of salt over the amount of gallons. The amount of gallons just isn't changing in this case because of the way the problem is set up. We can now go ahead and rewrite this and see that this is actually just a linear differential equation. So if we write this as x prime plus 5 over 100 is 1 over 20, x equals 5. That's a pretty straightforward linear differential equation. We can go ahead and find our integrating factor. It's going to be e to the integral of 1 over 20 dt, and that'll be e to the t over 20. Multiply everything here by that, so we have x prime e to the t over 20 plus 1 over 20 e to the t over 20x equals 5e to the t over 20. Go ahead and recognize your product rule on the left side there, so that is xe to the t over 20 prime equals 5e to the t over 20. And now go ahead and integrate that right side. We'll end up with just xe to the t over 20 on that left-hand side, and then integral of 5e to the t over 20. We'll pull that up here. When we go ahead and integrate that, we're going to have xe to the t over 20 is equal to 100 e to the t over 20. And then remember your plus c. We can go ahead and isolate x by multiplying both sides by e to the negative t over 20. So that'll get us x equals 100. Those terms cancel out, so 100 plus ce to the t over 20. sorry, that should be negative t over 20. Now, we're given an initial condition here because we know that initially, so at t equals 0, we're containing 50 pounds of salt, so x equals 50. So 50 equals 100 plus c e to the 0, because t is 0, that will always be 1. So we can solve this and see that c is equal to negative 50. Go ahead and plug that back into our original equation for x. We get x equals 100 minus 50 e to the negative t over 20. And now we're asked to solve for our point after 20 minutes, so that'll be t equals 20 because t is in minutes. And we get that x of 20 equals 100 minus 50 e to the negative 20 over 20. And that goes to 100 minus 50 e to the negative 1 when you simplify, and that is indeed answer choice E here. You're given a logistic equation. The first thing that we want to do is get a graph of what this looks like. If you remember how to go straight to that graph, go ahead and do that. But if you do not, you can always draw out your number line here, find our roots. This p is going to give us a 0. This p will give us a 100. And then we need to find our sign value of dp dt in each of these. So say plug in 1 for p, this will be positive, this will be positive 99, so this will be a positive in there. Below 0, this p is going to become negative while this 100 term stays positive, so that'll be negative. And then same thing above 100, we're going to have this second term become negative, so that will always be negative. And go ahead and draw our arrows here. We'll see that 0 is an unstable equilibrium, while 100 is a stable equilibrium. And what that logistic equation graph always looks like is an asymptote up at your carrying capacity, which is this number here, 100. And then we'll have a curve like that, and a curve like that. Now we can start taking a look at our true-false statements. If p0 is greater than 0, then the limit as t approaches infinity of p of t equals 100. This is true because we can see that no matter where on any of these lines we start, as t gets greater, we always approach 100. We're never actually going to reach it because it's asymptotic, but we do indeed approach 100 in the limit. If p0 is not 100, then p of t can never equal 100 for all t greater than 0. This is also true because of what I was just saying. We approach asymptotically, but this line will never actually reach 100, so this is a true statement. And then number 3 is saying that if p0 is between 0 and 100, for a time greater than 0, we can find p of t equals 0. This is not true because we can see here that this is also never going to actually reach 0, at least with t greater than 0. It may approach it asymptotically further back, but we again never reach it, just like we never reach 100 up here, so that statement is going to be false. We cannot find a t. So 1 and 2 are true, 3 is false. That gets us answer choice D. Number 6 is another homogeneous equation, which means we need to go ahead and use our characteristic equation to solve this. So go ahead and start substituting in our r's. We get r to the 4th plus 8r squared plus 16. Don't make the mistake of putting an r there, because it's y to the 0th derivative. Don't put an r there. That would be y prime, and set that equal to 0. If you can solve this, go ahead, but you can also go ahead and substitute in u equals r squared. That gets you u squared plus 8u plus 16 equals 0. You can factor that into u plus 4 squared equals 0. We see that u has to be equal to negative 4 with a multiplicity of 2. That multiplicity of 2 comes from this square here. But now when we go substitute that back in, we find that negative 4 equals r squared. So therefore r has to be equal to plus or minus 2i, again with a multiplicity of 2. When we have imaginary solutions like this, we know that our set of solutions will look like cosine 2t. This 2 is coming from the coefficient of our i there, just sine of 2t. And then to account for the multiplicity of 2, we have to get a set where we multiply each term by t as well. So we have a t cosine 2t and a t sine of 2t. And that gets us our fundamental solution set, which is the same as the set listed in option A. 7's another homogeneous differential equation because our right side is 0. So go ahead and start plugging in our r's. We'll get r squared plus 6r plus 34 equals 0 for our characteristic equation. You can either complete the square here or use the quadratic formula. I'm going to use the quadratic formula. So you'll get negative 6 plus or minus the square root. 6 squared is 36 minus 34 times 4, which is 136, all over 2. This will become negative 6 plus or minus the square root of negative 100 over 2, and that's negative 6 plus or minus 10i over 2, and then simplify that to negative 3 plus or minus 5i. When we have a term that looks like this, we have both our real part and an imaginary part. We write that as y equals e to the negative 3t from that real part times c1 for our first unknown coefficient, cosine 5t coming from that imaginary part, plus c2 sine of 5t. So now we have our two unknowns. We're given two initial conditions, one in y prime, so we'll know that we are going to need to find y prime in order to solve this. I'll go ahead and do that now. Y prime, go ahead and use product rule on that. It becomes negative 3e to the negative 3t times all of this stays the same. And then plus the first term stays the same times the derivative of the second. So in there, that'll be negative 5c1 sine 5t plus 5c2 cosine of 5t. All right, our first initial condition in y is y of 0 is equal to 4. So we'll go ahead and set 4 equal to e to the 0 is 1, so that term disappears. And then we have c1 cosine of 5 times 0 is cosine of 0. Cosine of 0 is 1, so that becomes just c1 times 1. And then our sine term is going to disappear because sine of 5 times 0 is sine of 0, which is 0. So this just straight up tells us that 4 is equal to c1. c1 equals 4. Great. And then we need to go ahead and use our derivative equation, our y prime equation, to find our other unknown. So if we go ahead and substitute 0 in for that, we know it'll be equal to negative 10. So negative 10 equals, again, e to the 0 is 1, so that'll just be negative 3 times, and then cosine of 0 is 1. So c1 sine term disappears because sine of 0 is 0. And again, we have 1 times negative 5 c1. That term will disappear because it's a sine. And we have 5c2. That term, the cosine will just become a 1 because it's cosine of 0. We can go ahead and plug in our known c1 there. So negative 10 equals negative 3 times 4 plus 5c2. That becomes negative 12. When we add that to the other side, we have 2 equals 5c2. And therefore c2 equals 2/5. Now we need to write our actual y equation, so we come back up to our regular y, and we just plug in our sieve terms that we found. So y equals e to the negative 3t times c1 we found was 4. So 4 cosine 5t plus 2/5 sine of 5t. And now let's go see which answer choice matches that. Looks like they just multiplied out in answer choice B, but that matches. So our answer here is choice B. In problem 8, we're asked to find a value for alpha, which makes this equation exact, and then our implicit solution to the IVP. So remember, to determine exactness, we need dm dy to be equal to dn dx, where this term here is m, and this term here is n. Our dm dy is going to be alpha x plus 5, and then our right side becomes 2x plus 5. Canceling out the 5 and the x shows us that alpha is equal to 2. So that's the first part of our solution that we'll then go ahead and plug back in to get our implicit solution. Remember, that implicit solution will come in the form of big F x y is equal to a constant c. And what we want with big F is so that the partial derivative in terms of x is equal to this m term, and the partial derivative in terms of y should be equal to this n term. Easiest way to start off there is to integrate your m term in terms of x. So go ahead and plug that 2 in for alpha. We get the integral of 2xy plus 5y dx, and that is equal to x squared y plus 5xy. And instead of a plus c, we're going to write a plus h of y, because that h of y term can be anything in terms of y. It won't affect our derivative in terms of x, and we'll need to fill that in later. So that's big F. We now need to make sure that our derivative in terms of y ends up being this n term. So we'll go ahead and find that partial derivative, which will be x squared plus 5x plus h prime of y, and then compare this to your given equation up here, and we see that h prime of y has to be equal to negative sine y. Integrating that gets us that h of y is equal to just cosine of y, and then we could go ahead and plug that back into our implicit solution here, our big F. So x squared y plus 5xy plus that h of y, which is cosine of y, is equal to our constant c, and that's where we account for that constant of integration. So this here is our general solution, but we're given an initial value and asked to find a particular solution. We can go ahead and plug in 1 for x and y for 0. This first term becomes 0, so does this second one, and then cosine of 0 is 1. So we find that c is equal to 1, which means we can write our particular solution as x squared y plus 5xy plus cosine y equals 1. Again, we're just plugging in that 1 for our c here from our general solution, and this is your final particular solution to this problem. These reduction of order problems in number 9 are one of the longest types you'll come across on exam 1, but they're not that difficult, just a lot of math. So they're telling us here, they're giving us one solution to this differential equation, and they're reminding us of the reduction of order formula here, that we can find another solution using v times y1. So we'll go ahead and set this up as y2 equals v of x times y1 is x to the 5th. This is reminding us that v is also a function, so we have to keep that in mind when we are taking the derivative of this. We need to get our first and second derivatives of this y function so that we can go ahead and plug it in back up here. I'm going to drop the x from the v's, but remember it's still there and we have to account for it. So using product rule on this, we will get 5x to the 4th v plus x to the 5th v prime. And our second derivative is going to be 20x cubed v plus 5x to the 4th v prime plus 5x to the 4th v prime plus x to the 5th v double prime. We can go ahead and combine some like terms here and get 20x cubed v plus 10x to the 4th v prime plus x to the 5th v double prime. Now we can go ahead and take these three derivatives of y and substitute them into our original equation. So we'll go ahead and do that. We have x squared times y double prime, which we found to be 20x cubed v plus 10x to the 4th v prime plus x to the 5th v double prime. And then we have minus x times our y2 prime and minus 15 times that original y, which is vx to the 5th, and that remains equal to 0. Now we can go ahead and multiply this out to hopefully simplify it a little bit. We'll get 20x to the 5th v plus 10x to the 6th v prime plus x to the 7th v double prime minus 5x to the 5th v minus x to the 6th v prime minus 15 v x to the 5th equals 0. When we go ahead and look for our like terms, we'll start with the highest powers. We only have one x to the 7th term, so we'll have x to the 7th v double prime. Our x to the 6th terms will have the 10. We've got a 10 here and a minus 1 there, so we'll have plus 9x to the 6th v prime. And then our x to the 5 terms here are going to cancel out because we have a plus 20 and then a minus 5 and a minus 15. So we're actually just left with these two terms, which makes this quite a bit simpler. So now we have to go ahead and solve this for v. We can go ahead and move one term over to the other side. And because it's given to us up here that x is always greater than 0, we can eliminate x's without worrying about losing solutions. So we can simplify this to x v double prime equals minus 9 v prime. We just canceled out 6 of those x's. We can go ahead and separate variables, and we'll get v double prime over v prime equals negative 9 over x. And then when we integrate both sides, this left side is going to become the natural log of v prime. If you're not seeing why that is, you can go ahead and do a u substitution with u equals v prime, and you should end up with that result. And then this side will become negative 9 ln x plus c. Don't forget your constant there. When we go ahead, we can take both sides, we can exponentiate both sides, so we'll end up with v prime equals e to the, we're going to move that x up into the power using our log rules, plus e to the c. And then using our power rules there again, we'll get v prime is equal to c1 x to the negative 9th. Remember, we're just combining this constant term that would get added up here down in front. It's just c1 because it's a different c than that initial c we were using. We can go ahead now and just integrate this to find v. So v equals the integral of c1 x to the negative 9th. And when we integrate this, we'll get v equals, we can actually collapse this coefficient that's going to be in front of the x into one new coefficient. We'll call that c2 x to the negative 8 plus, we'll call that c3. Because we're only asked to find one of our infinitely many solutions for v, we can choose these two coefficients, c2 and c3, to be whatever we want. So in order to keep it simple, we will choose c2 to be 1 and c3 to be 0. So we'll end up with v equals x to the negative 8. Now remembering where we started all the way up here with y2 equals v times y1, we can rewrite y2 equals our v from down here, so x to the negative 8. And then remember the y1 that we plugged in was x to the 5th. And that gets us y2 is going to be equal to x to the negative 3. For number 10, the first thing we have to do is get this equation into homogeneous form. So it's telling us to use the substitution that we usually do. V is equal to y over x. We can go ahead and rewrite that as y equals vx. And we're going to need both y and y prime in order to plug back into this equation. Remember to use product rule on this when you take the derivative. So y prime is going to be equal to v prime x plus v, because v here is a function. We can now go ahead and plug this back into our initial equation back up here. So x squared times that y prime we just found, v prime plus v, minus y squared, so that's going to be v squared x squared, minus x times that y, so that's x squared v, is equal to 0. Multiply this out, we'll get x cubed v prime plus x squared v minus v squared x squared minus x squared v equals 0. These two terms cancel out, and we're left with x cubed v prime minus v squared x squared equals 0. We can now go ahead and separate this and start solving for v. So we'll have x cubed v prime is equal to v squared x squared. We can go ahead and cancel out some of our x's, and we'll end up with just x v prime equals v squared. I like to rewrite this left side as x dv dx equals v squared. I think it helps us remember what's going on here. Now you can see that we can pretty easily separate variables here. This will become a 1 over v squared dv equals 1 over x dx. Go ahead and integrate both sides now. We'll end up with negative 1 over v is equal to ln x plus a constant. We can combine the constants from both sides into just one side here, into one collective c1. If we go ahead and substitute back in for v on this left side, we're taking the inverse, so that'll become negative x over y. Again, we're just using this v substitution that we initially did, is equal to ln x plus c2. We can now go ahead and isolate for y by switching around our sides here. You're going to end up with y equals, that'll be negative x over that right side. Now we have a general solution for y, but we're given an initial value up here, so we need to go ahead and find a particular solution. You could plug this into this y here. I actually think it's a little bit easier to plug it in the second to last step. So we're going to go ahead and find our particular solution by plugging in 1 for x and 2 for y. So negative 1 over 2 equals ln of 1 is just 0, plus that c2. c2 is therefore equal to negative 1/2. We can go ahead and substitute that back in down here and end up with negative x over ln x minus 1/2 as our final solution.